Hi, and welcome to Bridging the Trust Gap with Ethical AI. My name is Gabriella Lio, and I'm a data scientist at Sense Corp. I've worked with multiple Fortune 500 companies, sharing and implementing a lot of data-driven solutions. I have a lot of experience building and deploying machine learning models, and I serve as a thought leader within my company, promoting ethical AI at every step along our clients' journey to adoption. I'm excited to be speaking with you all today on this topic, so let's go ahead and dive right in. So firstly, I'm going to start with a quick overview about the importance of ethical AI and why ethics need to be seen as an important practical consideration for anyone who is using and building machine learning systems. Then I will jump into 3 examples of failures surrounding ethical AI and move into 7 tips around how to bridge the trust gap and build ethical AI. This will focus on both organizational and programmatic solutions, and then I'll be wrapping up the talk with a walkthrough and a live example of a Python library you could start using today to implement ethical AI in your models. So let's take a step back and look at why ethical AI matters. There are 2 aspects here that we really need to focus on. It matters to the business and it matters in our models. For the business, we are in the age of AI. Most organizations are racing to adopt AI, and with that comes the added responsibility of being accountable for what they do and how they behave. If they want to generate trust from their customers, partners, and the public, they need to have models that are ethical and that instill trust within their customers. Trust is a competitive advantage, so in order for your business to thrive, you need your customers to trust you. Now, your models can either harm or propel you when it comes to creating trust with your customers. So if your AI model is built without an ethical framework in mind, it's not like just making a single mistake. If the training data is biased, the mistakes will be compounded, and the algorithm will continue to learn from flawed data. So this in turn could lead to automated decisions and predictions affecting a person's chance of getting a loan, or maybe even failing to diagnose an illness or a disease. If the model is responsible for an incorrect decision, the trust from the customer is broken and you will likely lose their business. So these 2 aspects, trust in the business and trust in our models, go hand in hand towards creating and sustaining a successful organization. And to further prove this point, I'd like to call out a quote from a Capgemini report that was assessing consumer and executive sentiment regarding AI and ethical implementation around the globe. So the global survey was conducted from April to May of this year and included 2,900 consumers from 6 countries and 884 executives in 10 countries. And the quote reads, "The majority of consumers expect companies to be accountable for their AI systems, yet about half of the companies do not have a dedicated member overseeing ethical AI implementation." If the business knows that the customers are going to hold them accountable, then why isn't any action being taken on the organization side? And it's not like the executives in the business are unaware of the issues surrounding ethical AI. Actually, 65% of the executives surveyed said that they were aware of the issue of discriminatory bias within these AI systems, and a number of respondents said that their company had been negatively impacted by AI systems. So, for example, 6 in 10 organizations had attracted legal scrutiny, and nearly 1/4 had experienced consumer backlash within the last 3 years due to decisions that were reached by AI systems. But despite all of this information being out there, still only 53% of respondents said that they had a dedicated leader responsible for overseeing AI ethics. There's clearly a big misalignment between consumers' needs and how organizations are responding in today's marketplace, and that gap needs to be closed. And the issue doesn't only exist in regards to the business and its customers, it also exists within the organization itself. So from that same Capgemini report, it was discovered that while 4 in 10 IT and data professionals said they had detailed knowledge of how and why our systems produce the output that they do, only about 1/4 of the marketing and sales executives agreed. And furthermore, about 51% of marketing and sales executives said that they realized their AI systems sometimes make decisions which are incompatible with our corporate values, compared to only 40% of IT and data professionals responding the same way. So this also signifies that there's a lack of development of internal practices within an organization that is hindering the path to ethical AI. If within an organization, employees are not on the same page about ethical AI, the chances are slim that they're going to be able to generate trust around AI with their customers. So the problem needs to be fixed from within. And it starts by including ethical AI at every step in the process. So normally ethics are thought of only during the data and modeling phases, but in actuality, it starts at the very beginning when we are identifying the problem. You have to assess the impact that your model is going to have on your business and your customers before you even begin solutioning. It also helps to have diverse team members from different parts of the business included in these conversations instead of just AI developers to ensure that your organization's core values are in line with the proposed solution for the problem. Once you have identified the problem and have a solution in mind, you have to start collecting your data. Here you need to think about the sensitivity of the data being collected. You have to ask questions such as, does it make sense to anonymize some of this information? Who in the organization should have access to this data? How was the data collected? If it was from the web, are we being socially responsible with the information that we've scraped? Did we get data from survey respondents? And if so, was the population of the respondents representative of a diverse population? This is just an example of a few questions that need to be addressed in this stage. Now that we have our data, we start doing some exploratory analysis on it, right? So this is a major step where we need to look for potentially biased fields such as gender, race, or age, and we need to exclude them from the data set before we move into modeling. In the modeling phase, we have to make sure that we are creating an explainable model and that we are checking to make sure that our predictions aren't biased towards specific demographics. It isn't just enough to create a model that has 95% accuracy and call it a day. Just because a model is accurate doesn't mean it isn't spitting out biased predictions, so you have to create checks and audit your models before putting them into production. And it doesn't end there, right? Over time, models may drift or become stable. So you must make sure that you have statistical process controls running against your models, checking for this, as well as retraining your models every now and then on a more current training set of data. Once ethical AI is included in the entire process, then you will start to see firstly within the business that all your employees are aligned, and then externally that you are creating solutions in which your customers trust. We touched on identifying the impact that your model is going to have on the business and the customers, but I want to elaborate on why it's so important that we think about this before we start developing our models. Think about how AI is used in our day-to-day lives. We have models running on Amazon's Alexa that interpret what a user says and responds with an answer. In the grand scheme of things, if you think about the impact this tool has on people, it's pretty minimal. What happens if you ask Alexa what the weather outside is and she says 80 degrees when it's actually 60? The impact is that you're going to be cold when you walk outside, so I would say this is a pretty low impact tool. Let's up the stakes a little more though. We're all familiar with YouTube, and whenever you're watching videos, you get recommendations from an AI model on what videos to watch next, and that's related to your past preferences. So what happens if a child is on there and has suddenly taken an interest with a conspiracy theory like the Illuminati? After that, the YouTube's recommendation engine starts recommending a plethora of conspiracy theories to this 9-year-old child. The impact of this tool is far greater than Alexa's because instead of just giving a wrong answer, it's spreading false information and fundamentally shaping a child's viewpoint. And if we want to take it to the extreme, some tools such as models that are used to predict or decide someone's sentence in court have a very high impact on someone's life because if the model produces an incorrect decision, that person's sentence could be 50 years instead of 10. So the impact is very specific to the problem at hand that is trying to be solved. And if this is an afterthought instead of a forethought during your problem identification, your AI models will surely fail to be ethical. And here are 3 examples where it was clear that ethical AI was not a forethought. So let's take a look at the first one. In 2015, Amazon created a computer vision recruiting tool that was used to scan resumes. The idea was that it would automate this process for recruiters and give them a short list of the top resumes. Well, before the model made it into production, they discovered that it was biased against women. Since the training data over the past 10 years had been predominantly male resumes, coinciding with the historical trend of a male-dominated tech industry, the model taught itself to penalize any resume which had the word women in it, such as women's college or a women's chess club and so on. Another example was in 2016, when ProPublica studied the outcomes of a software being used in the US courts. The software being studied was a computer program that was used to spit out a score predicting the likelihood of a person who had been booked of committing a future crime. By studying what the algorithm predicted and comparing it to what actually ended up happening in the real world years later, they found that the algorithm was particularly likely to falsely flag Black defendants as future criminals, wrongly labeling them this way at almost twice the rate as white defendants, and it found that white defendants were mislabeled as low risk more often than Black defendants. Our last example was more recent in 2019, and it highlights the concept of explainability in our models and why it's necessary. A man went in to apply for credit at his bank. After his application got denied, he asked the reasonable question, why? The reason they gave him was because he was a Finnish-speaking man in a rural area. Most of the time, algorithms in the financial industry are making decisions autonomously. The person held responsible for the decision might not have the time or the skills to familiarize themselves with these models at hand, and therefore fewer than 1% of the time decisions are revised. If these people understood the models they were using, they could explain the outcomes of the model, and the customers wouldn't be left questioning the decision. It also highlights the need for human intervention at times when these models are being used to check that they're producing the right output. So maybe the data in the model wasn't trained on having an example of a Finnish-speaking man living in a rural area, and therefore it came to an incorrect decision. But unless we have that explainability of how our models came to a specific decision, we won't be able to pinpoint why the decision was incorrect. So now that we know that ethical AI is an issue that consumers in the marketplace care about, and that all organizations are not making an important focus area, how can you help your organization become aligned on an ethical AI strategy? I'm going to walk you through 7 steps that will help you bridge the trust gap and create ethical AI not only within your organization, but for the customers as well. Let's start with the first step, assessing the potential for ethical risk and setting up algorithm controls. We touched on both of these things when I talked about including ethical AI at every step in the process. The risk evaluation comes in the problem identification stage when we talk about the impact of our model. You need to perform these ethical sweeps at every step in the process to evaluate the solution's vulnerabilities. And a big part of this is in the modeling stage. You must evaluate various models designed for balancing between fitting bias and variance. And this also includes checking your predictions after the models are in production to make sure that your models aren't becoming stale or drifting. Secondly, you must set up a diverse development team. This also happens in the problem identification stage. And I don't just mean that you have diversity in your IT developers. Although that is a great step, it's not enough. You need to be including people on the business side, maybe in sales, marketing, even supply chain, dependent on what the specific problem is. And then you even need to think about including employees from legal or HR. Everyone will have a different viewpoint, and together you can all catch some of those vulnerabilities you may not have even thought of with just your own IT team. If the diverse talent doesn't exist from within, this is where you would need to create an environment that allows you to hire or subcontract with diverse participants. The third step is to create a policy guide. If you want everyone in your organization to be on the same page about ethical AI, your organization should define their position related to AI technologies and communicate this through a policy statement or at minimum a set of guidelines. What happens if a user of an AI model within your organization realizes a model is making a flawed decision? What avenues do they have available to them to report this? That's just one example of an issue that could be solved with a policy guide. Making it known across the company that the organization has a stance on ethical AI isn't enough if avenues don't exist to ensure that that stance is being met. The fourth step is taking the time to educate AI teams. These conversations are not easy, but they have to be had, and it helps if it's done as a team or as a division. You could require employees to participate in an ethics in AI course, or you could have someone come in and conduct a workshop around it. It also helps if the team themselves are presenting internally on ethics topics, so they are not only talking the talk, but they're walking the walk. At my company, we have bi-weekly knowledge shares for our data science team, and multiple times we have discussed ethical AI in these sessions and its implications in our work. You could show an example of when you found a biased field in your data set, or maybe demonstrate how to use a new tool or technology that helps with the explainability of models. The fifth step is to track and participate in industry regulations. As an organization, you should be complying with all of the global regulations such as GDPR, ethics guidelines for trustworthy AI, and you can also support pledges that promote ethical AI such as the Safe Face Pledge and the Lethal Autonomous Weapons Pledge. So those past 5 steps were all things that you could do as an organization to promote ethical AI in the workplace. But a lot of times we don't have the power to enact these changes. We can be a thought leader and promote these practices and spread the word, but at the end of the day, the organization needs to enact these practices. As a tech user, though, there are some things that we can do immediately to promote ethical AI, and that is where steps 6 and 7 come in. So step 6 is around leveraging automated tools. You can leverage technology to evaluate AI systems for potential bias or flaws, to reduce the manual aspect of the task, and to ensure consistency in how the rules are applied. You can also use counterfactuals to increase the transparency of your models without revealing the underlying intellectual property. And lastly, step 7 is minimizing the bias in the learning data, which we had talked about earlier when including ethical AI at every step in the process. Here, we can create a bias hypothesis and then evaluate and test for bias in our exploratory data analysis. We can assess and recognize the data collection, sampling, and validity issues related to bias as well, so that moving forward, we have a better understanding of how to remove the bias before it even gets into the model. But as you're all Python programmers, maybe even data scientists who are creating AI models, I wanted to give you an immediate solution that you could start implementing today that gives you control over producing ethical AI within your team. And that solution is Shapley values. So SHAP is a Python library for modeling explainability, and it leverages the idea of Shapley values for model feature influence scoring. There are other Python libraries out there that do super similar things, which include Lime or InterpretML. And some other automated tools you could use to minimize bias and increase explainability are the AI Explainability 360 and AI Fairness 360 toolkits, which can be accessed through Python as well. They're all great tools, but today I want to focus on SHAP. I'm first going to walk you guys through an example of the calculation so you understand how the library works underneath the hood, and then I'll switch over to a Jupyter notebook and run through an example of using the library to explain some predictions. So let's start with what SHAP stands for. It stands for Shapley Additive Explanations, and the definition of a Shapley value is the average marginal contribution of a feature value across all possible coalitions. This uses a lot of jargon from game theory because it's a method from cooperative game theory that tells us how to fairly distribute the payout among features. Put simply, a prediction can be explained by assuming that each feature value of the instance, or row, right, is a player in a game where the prediction is the payout. So we're going to walk through this equation below with an example so that we can fully understand how the method works. So here's our use case. You're creating a machine learning model to predict condo prices. For a certain condo, it predicts that the condo is worth $300,000, and you need to explain this prediction. The apartment has a size of 50 meters squared, it's located on the second floor, has a park nearby, and cats are banned. If the average prediction for all condos is $310,000, we need to explain how each of these feature values mentioned above contribute to the prediction compared to the average prediction. So let's use our game theory jargon to frame this problem, right? So for our use case, the game that is being played is referring to a prediction task for a single instance of the data set, so known as a row. So we're going to compute Shapley values, right, at a row level. The gain is the actual prediction for this instance minus the average prediction for all instances. So in our example, that would be 300,000 minus 310,000. So our gain here is negative 10,000. The players in our game are the feature values of the instance that collaborate to receive the gain or predict a certain value. So again, in our example, the players are having a park nearby, cats being banned, the area being equal to 50 meters squared, and the condo being on the second floor. So these are all working together to achieve a prediction of $300,000. So the overall goal of this game is to explain the difference between the actual prediction and the average prediction, which that difference is negative $10,000. So what do we mean by explain? This means a possible answer could be that park nearby contributed $30,000, the size being 50 meters squared contributed $10,000, the condo being on the second floor contributed nothing, and cats being banned contributed negative $50,000, right? So if you add all of those up, our final contribution is negative 10,000, which is equal to our gain. So here we were able to explain, right, and distribute that payout among our players and explain why that condo prediction was $300,000 by looking at what each specific feature contributed to that gain. So those were made up payouts, but how do we actually calculate those values per each player or per each feature? And the answer is that we have to find the Shapley value of each feature. And if you remember the Shapley value definition, it's the average of all the marginal contributions to all possible coalitions. So how do we find that average? We'll first need to list out all of our coalitions. In our example, we're trying to find the Shapley value just for a cat being banned. We could have no features. We could have just park nearby. We could have park nearby and size of 50 square meters. So you're starting to get the idea here. You can see the list of all the possible coalitions up there on the right for our specific example, which is the cat being banned, right? That's the feature we're trying to predict a Shapley value for. So to make it simple, we're just going to start with one coalition. So let's use the one that's circled in red. Park being nearby and the size of the apartment being 50 square meters. If we want to simulate this coalition, we randomly sample from a donor row for the features that are not in the coalition, so such as, the floor feature. So the very first step is to randomly sample a donor row and use that information to fill in the gaps. Then we predict the condo price. So for this specific coalition, park nearby and 50 square meters, with the random values from the donor row, we get $310,000. Now what we do is remove cat banned and replace it with the value of cat from the donor row. So in this case, the random value is cat allowed. Now we predict the price of the condo and we get $320,000. So we see that that marginal contribution of a cat being banned was negative $10,000. Since we just sampled from one donor row, right? That's a very small sample set. So what we need to do is pick a new donor row and go through the exact same steps we just did, ending with finding the contribution. And now we would take the average of those two contributions. So the estimate that we get depends on the values of the randomly drawn donor row. So in order to get a better estimate for these Shapley values, we need to repeat this sampling step multiple times and average all of the contributions. Now remember, that was just for an example of one coalition for cat banned. But as you can see, there are multiple coalitions for just the feature cat banned. So we repeat this computation and process for all possible coalitions of cat banned. That means we predict the condo price with and without the feature value cat banned and take the difference to get the marginal contribution. And at the end, that Shapley value, back to that definition, is the average of all the marginal contributions to all possible coalitions. Now that definition makes sense in your head, but you're starting to imagine, whoa, this computation time is going to increase exponentially with the number of features, especially with that sampling that's going on. So to keep computation times manageable, you must compute contributions for only a few samples of the possible coalitions. So what does SHAP, the Python library, output actually look like when implemented in Python? So it essentially can take a black box model with its feature inputs, base rate prediction, and output prediction for one row or instance, and then it will explain exactly why that prediction was made by showing the payouts from each feature or the feature's Shapley values. In this example, the base rate was 0.1, and the prediction that came out was 0.4. So how did we come to that prediction? Why did it have a gain of 0.3? So you can see that BMI being equal to 40 was responsible for 0.1 of that increase from the base rate, and so was BP being equal to 180. But sex being female bumped down that gain by negative 0.3, and then her age bumped it back up by 0.4. So if you add up all those values together, you see that the overall prediction increase from the base rate is 0.3, and you know exactly how much each of the features contributed to that increase. In this case, you could say that age was the most important. SHAP has great documentation online, so you can dive deeper into this, but I just wanted to show you that it works on a variety of models. It has explainers specifically for trees, gradients, or deep learning models, and then it has a catch-all explainer called kernel explainer that explains the output of any function. And it also has different types of plots that you can look at for the outputs. So I'm going to show you guys what this looks like for different models using the Titanic data set. So we're gonna go ahead and hop over to my Jupyter notebook. So in here, all I have to do is import sklearn, my train test split, pandas, numpy, shap, and then time because I was timing it earlier. I do some data cleansing here, right? I drop any rows that have null. It wasn't that many, and then I decide just to not even use cabin as a field. So now I have my cleaned up data set, and I do a little bit of feature transformation, right? So I pull out of their name, their title, because this has been shown to be a feature that has a lot of influence in this Titanic data set. So whether they were named a miss, a mister, a master, right, affected their chance of survival. And then I create a train, my Y train set and my X train set. And here's just a little snippet of what my final training set looked like, right? So I have the P class, which is their ticket class. I have their sex, male or female. I have their age. I have how many siblings or spouses they had aboard Titanic and how many parents or children were aboard. I also have the amount they paid in, money for their fare. I have what port they embarked from, and I have their prefix that I pulled out, right? Miss or Mr. And I also have whether they survived or not in my Y train. So here I'm just setting up my data again, doing a train test split. So now I have my training and my test sets. Now we get into the modeling. So I wanted to do KNN, a neural net, and then a random forest just to show you guys that Shapley will output different things for different models because models score features different ways, right? So here we're using sklearn, we're doing a K nearest neighbors model. That accuracy is 66%. So not too great on the test set, right? But what I want to show you is what Shapley would tell us. So we know that our model is not that great, but we also want to know exactly why it predicted something for a certain row. So remember that we're computing Shapley values for a specific instance or row in the data set. So I'm using the kernel explainer here. I'm calling the Shap library. I'm giving it the model that I want, right? The model that I initiated above. And I'm telling use the X training set as that data set that you're going to sample from for those donor rows. Then I'm saying grab the first row in the X test set and using that explainer that I just set above, produce the Shapley values for that specific row. And the way I want to see it is using the Shap force plot. So I pass it the expected value, right, that base rate. I pass it the Shapley values, and I pass it the actual values from the row. So this is what the force plot looks like. So you can see what the base value was, and then you can see what the output started at. If it's in red, it means that it made the prediction go higher. So here we were predicting if this person was going to survive or not. So this is the survival class that we're looking at. And so you can see here that, their sex, they were female, they were 24, and they paid a high fare, right? So we predicted that they would have a 60% chance of survival, and that's looking at it from the force plot. If you want to look at it from the waterfall plot, that helps a little bit more in seeing exactly, how important that specific feature was because it increased it by 0.18. I mean, here you could kind of do the math yourself. You see that fare is the most important, but you don't know specifically by how much. So again, our base rate was starting at 0.37 something, and our prediction was 0.6, but you're seeing for each one in this waterfall plot exactly by how much it went up by. Here is another example. This is the 15th person in the data set, right? We're looking again if this person would survive. They were a male, they were 32, and they paid a very low class. So the KNN model predicted that they had a 0% chance of survival. Again, we have that force plot and that waterfall plot. You can also explain all the predictions in a test set with Shap. It takes a very long time to run, as you can imagine, but it basically averages all of the Shapley values per every single row that it calculates it for. And so what you get here is a plot of the most important features over the entire data set. So you see for class 0 and class 1, they're weighted the same, right? They have the same importance, but fare was the most important feature in this case for deciding if a person was going to survive or not for a KNN model, as well as age and then their sex and so on and so forth. You also have these really cool things called dependency plots. So you can show, right, here we're showing the scale or the range of the fare, right? So it could go from anywhere from 0 to 500. And on the y-axis, you see what the Shapley value was for that specific instance, right? So it's just showing you that on a plot. But what it also shows you, I didn't specify what feature I wanted it to show me the dependence against. So it did an auto and it chooses the one that had the highest dependence. But in this case, it was Mr. And you can see if it's 1, that means that they were a Mr., so they were a boy. If not, it's 0, so they were not. So you can see here, right, most people that paid a low fare did not have a high chance at surviving, right? There were a lot of them down here that had negative Shapley values. So even if they had a low fare, right, that Shapley value was going to be low. You see a bit more women up here, right? It looks like most of the men are down here. And then you see as you get to the fare being more expensive, almost all those people starting at 100 had those higher Shapley values, which means that they had a higher chance of surviving. So we see here that fare plays a pretty important role, and not so much here with the Mr. or the Mrs. Again, here we're looking at age. So we have that range of age on the bottom, and then we have the Shapley values per every single prediction or per every single instance, and you have that dependence against the Mr. So that was the KNN model. Now we want to look at a neural network. So our train was 84%, our test was 79, a lot better than KNN. Let's see what it showed were the most important factors using this neural net model. So we see that the base value was 0.39 for that same person, right? Predicting that same class, whether they would survive or not. But this time, instead of a 60% survival rate, we said that they had a 98% survival rate. And we have that force plot and we have that waterfall plot. And then in contrast, you see we have both colors here now. When we did the KNN model, you only had one color. It was blue, bringing it down. But we do see here that their siblings, right, being 0, increased this a little bit higher for them to survive. But still, this person, instead of having 0% survival from the KNN model, had 0.07% of survival from the neural network model. So it's good to see that different models have different Shapley values, right, because they weigh things differently. And again, you can explain all the predictions in the test set. So if you remember from above, fare was the most important, but here Mr. is the most important. So whether they were male or not, if they had that prefix, and then the class that they were in. So P class 1 was the highest ticket class, P class 3 was the lowest. So you see that those play a really important role in this specific model. So we're increasing that explainability, right? So for the overall predictions, we have this, but we also have per specific. If you needed to tell someone why that specific prediction was made, well, you have that explainability now. And we have these dependence plots. Here you can see a really cool pattern. So when looking at age versus P class 1, so being the highest class, you see that those between 0 and 10, so those that were really young, they all had a really high Shapley values, right? So they had a higher chance for survival. And it didn't matter whether they were in the first class or they weren't, because they were young, they were going to be saved. Meanwhile, if you look down here, the 40 between the 70s, the first thing you noticed is that most of those people were in the first class if they were older, right? And you also notice that it doesn't matter if they were in the first class or not. That didn't affect their chances of survival. It actually, made it worse if they were older because they had a negative Shapley value associated to them. So those dependence plots are really cool as well. And then lastly, just to show the third difference, right, I did do a random forest. It overfit a little. The train was 92, but the test was 77. And again, we looked at the single predictions, right? So we looked at that first person. Here they had a 97% chance of survival. So one lower than the neural net one. And we have that waterfall plot and that dependence plot. Here, sex seemed to be the most important. And then we have that other person, the 15th person in the data set, right? They had a 0.02 chance of survival, so lower than what the neural net said. And you see that Mr. played a really important role, male, those are pretty much the same. And then explaining all the predictions in the test set. Here, they thought the sex was the most important, and this one also thought that the P class, whether they were in the first class or the third class, was also pretty important. So this one was a little bit more similar to the neural net. Okay, so that is all I have for you guys today. Thank you so much for listening in. I hope that you guys will be able to implement this and use this in your models for explainability. For any questions, please email glio@sensecorp.com, and all my code is available at that link right there in my GitHub in a Jupyter notebook. So you can go ahead and download it and use whatever you need. Again, thank you so much and enjoy the rest of your day.